Hello everyone. We're going to try and solve a problem that we've encountered with multiple recurrences. And we're going to solve it actually by analyzing a problem we've already solved. So here I have a problem we've solved before. This is looks like a single recurrence problem, but let's start with an observation. Note that t of n is equal to, I could rewrite 2t of n over 2 as t of n over 2 plus t of n over 2 plus cn. Here we have two recursive calls. We have the first recursive call over here, underlined in green, and the second recursive call over here, underlined in purple. I'm going to have to designate something over here at the end, this plus cn. I'm going to call the additional cost, or the cost. We are going to try to analyze this with something called a recursion tree. Want to analyze with a recursion tree. So, let's do it. The recursion tree is a visual representation of how we are computing this value. So to compute t of n, I must compute two copies of t of n over 2. We're going to visualize this with a tree. So we have t of n as a base of the tree. In order to compute t of n, I need t of n over 2 and I need t of n over 2. This looks silly for this problem because those are the same. In general, they won't be, though. And how could I possibly compute t of n over 2? Well, I compute that via the same method as t of n. So to compute t of n over 2, I would plug n over 2 into the original expression there. So that's t of n over 2 equals t of n over 2, which is n over 4, plus t of n over 4, plus cn over 2. So I'm going to need to compute two copies of t of n over 4. So I have t of n over 4, and I also need to compute t of n over 4. And the same thing is true for my right branch here. I need to compute t of n over 4, and I need to compute t of n over 4. I'm going to modify this tree. So let's first copy it. Oops, undo, don't do that. Let's first copy it and then paste the tree. I'm going to modify it here. Let's get rid of this and move the tree around. All right. So I'm going to replace all of these recursive calls with their cost. So t of n, the cost, which I underlined before in purple, or not purple, orange, is cn. The cost for t of n over 2 is cn over 2. The cost for t of n over 2 is cn over 2. The cost for t of n over 4 is cn over 4. The cost for t of n over 4, cn over 4. The cost for this one is cn over 4. And the cost for this one is cn over 4. So let's draw that in a less messy way. In order to compute this, I need to compute the first thing, t of n, which requires cn. I then need to compute two copies of t of n over 2, both of which cost cn over 2. From there, I need to compute two more copies, which are cn over 4 for each of them. I then need to compute 2 copies for each of those, each of which will be Cn over 8, 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 and Cn over 8. And then I would do that again, each of which requires 2 copies. And I would keep doing this until eventually I've divided my size of my problem by such a large amount that eventually I no longer need to make recursive calls and I arrive at my base case. And that will happen for every single one of these branches. I will eventually get to the base case for every single one of my recursive calls. We analyze a recursion tree. This is what we call a recursion tree, a visual representation of the cost of each recursive call. We analyze it by computing the cost at each level. The cost to compute the root of this tree was Cn. That is the cost of the first recursive call. The cost of the second level of the recursive tree is adding up the cost of each of the nodes that appear there. So it's Cn over 2 plus Cn over 2, which is Cn. The cost at the next level of the tree is the sum of the costs cost of each of the nodes on that level. We have Cn over 4 plus Cn over 4 plus Cn over 4 plus Cn over 4. That's 4 copies of Cn over 4, so that's Cn. The level below that, we have 8 copies of Cn over 8. Again, Cn. I'm not great at patterns, but I'm pretty sure that for every single one of these levels in this tree, the cost is Cn. The orange here is the cost of the level. That's the cost of each of the recursive calls of that size. So, if that's the cost of each of the recursive calls, I want to know what is the total cost. The total cost is the sum of the cost at each level. So this would be the sum of the cost over all of the levels. However you want to write this down, whatever you want to remember, that's what we're doing. So we want to add up all of those copies of Cn. We have Cn plus Cn plus Cn. So this equals, in our case, Cn plus Cn plus Cn plus Cn plus a bunch of copies of Cn. We need to identify how many copies of Cn. If we go back up to the tree and look at it, the number of copies of Cn is actually the height of the tree. Number of copies of Cn is the height of the tree. The way we can compute the height of the tree is we want to know how many times do we need to make a recursive call to arrive at the base case. So we want to know the size of the recursive call at each level of the tree. How can we compute that? We already actually have all of the work done here. The cost at each level, the size at each level. The base was n, then n over 2, then n over 4, then n over 8, then n over 16. The size of the recursive call at each level, at level I, the size of the recursive call, the size of the recursive call is n over 2 to the I. It's n over 2, n over 4, n over 8, n over 16, a bunch of n over powers of 2. So, if we wanted to know how long does it take to terminate, we'd want to solve when does n over 2 to the h for the height of the tree, and I'm going to use that instead of I, equal the base case. Because that's when we finally end this division. If we scroll up, the base case was t of 1 equals c. So when does n over 2 to the h equal 1? Let's solve that for h. We get h equals log base 2 of n. So the height of this tree is log base 2 of n. So over in my problem I was looking at before, how many copies of Cn were there? There was h copies, and h is equal to log base 2 of n. So I'm adding up Cn log base 2 of n times. So this is equal to Cn times the number of occurrences, which is log base 2 of n. So the total cost, which we usually called t of n, the total runtime, is Cn times log base 2 of n. Hey, that's enough to get me my complexity. T of n is in theta of n times log n. This problem that we learned a lot of things along the way, so it might seem like that was complicated. Thankfully, this is really straightforward. All we're doing when building the recursive tree is plugging in the size of the problem into the recursive calls. So we have to build the recurrence tree, this tree here in black. We build that by continually plugging in the size of the problem, n over 2, n over 4, into the cost that we have for each recursive call. For most students, they seem to find this really difficult until suddenly it's really, really easy. So if this example is difficult, I recommend watching some of my other videos before we panic about understanding it. But this problem is a nice visual way of performing our substitution method. And we will see several other examples.